So, hi everyone. Welcome to the PCD of today's Codeforces Round 1000. And we will discuss the first four problems. Like, we will discuss the logic and code of the first three problems. And I'll tell you the logic of the D problem. And I'll like send the code in the description. And you can check it out from there. Because currently it is giving some bug. So, I'll discuss the logic. All right. So, yeah, let's get started with the problem number A. Just to confirm, I am audible right now, right? Just give a yes in the chat if I am audible. Okay, thank you. So, all right. The first problem says that a segment of positive integers L, R is called coprime if L and R are coprime. Okay. A coprime segment is called a minimal coprime if it does not contain any coprime segment not equal to itself. So, like basically, there's a segment. Okay. So the segment is L, R. This is like a range of numbers on the number line, right? This is L, this is R, and this range is called the segment, and it is coprime if and only if GCD of L and R is 1, right? And they are calling it minimal coprime if there is no coprime pair inside this also. Like this L, R. Suppose it is 2, 5. Okay. So in this, actually, there is like 3, 4. Like this 2 comma 5 is coprime, right? But it is not minimal coprime because there is one 3 comma 4 inside of it, and this is also coprime. So therefore, this 2 comma 5 is not minimal coprime. 2 comma 5 is not minimal coprime. Okay. So that's what the definition of minimal coprime is. Given L and R, a segment of positive integers, find the number of minimal coprime segments contained in L, R. Okay. So the problem says that we are given L and R, and we have to find the number of minimal coprine segments in that segment. Okay, right? So basically, let's take a sample. Okay, so there is like 1 comma 2. So just a minute. Okay, yeah. So 1 comma 2, right? Now we want to find the number of minimal coprime segments inside that, right? So in this case, one of them would be 1 comma 1, right? Because its GCD is 1, and nothing else is inside of it, which is minimal coprime, right? And other one would be 1 comma 2. Okay, because it is also coprime. Just a minute. Sorry, it is just 1 comma 1, right? The answer is 1, because this is the interval which is minimal coprime. So in this 1 comma 2 range, there is only 1 comma 1 interval which is minimal coprime. All right. Then let's look at 1 comma 10. Okay. So this is 1, this is 10, and in between there are some numbers, right? So in this case, 1 comma 1 is a coprime segment. 1 comma 2 is not, like it is not minimal. Like 1 comma 2 is not a minimal coprime segment because it contains a 1 comma 1 in it. Like basically we want to count the minimal coprime segments, right? So actually 1 comma 2 is not minimal coprime segment because it contains 1 comma 1, which is minimal, which is a coprime segment, right? So therefore 1 comma 2 is not a minimal coprime segment. Then if you look at 2 comma 3, then it is minimal because all the subintervals like 2 comma 2 or 3 comma 3 both are not coprime, right? So therefore 2 comma 3 is a minimal coprime because it doesn't contain any other um, segment inside of it which are coprime, right? So 2 comma 3 is coprime, 1 comma 1 is coprime, then 3 comma 4 is also coprime, and so on. So we get up to 9 comma 10, it is coprime, minimal coprime. Actually, as you can see that any two consecutive numbers x and x plus 1, they are always coprime, right? That's what the observation here is. So that's how you can say that in any interval that is from L to R, you can have like L plus like L. It will the intervals will start from um, L comma L plus one, L plus two, sorry, L plus two comma L plus three, and so on up to R, right? Up to R minus one comma R. So you can easily count that this is just R minus L number of pairs, R minus L number of intervals, right? And they are minimal also because if we take like suppose if we are taking x and x plus 1, right? I am claiming that x and x plus 1 is always a minimal unless x is not equal to 1 here. If x is equal to 1, then it is other case. But if x is greater than 1, then I'm claiming that x and x plus 1 is minimal segment. That is because x comma x cannot be minimal, and x plus 1 comma x plus 1 also cannot be minimal. I mean, it cannot be coprime, right? X and x plus 1 is minimal coprime because all of its subsets. This is one subset and it is not coprime, and this is also not coprime, right? So therefore, any two consecutive numbers are form a coprime segment, right? So that's how we can say that um, in any given range L to R, you can find R minus L segments. And actually, in the samples also, you can observe that like 2 minus 1 is 1, 10 minus 1 is 9, this is 0, then 420 minus 69 is 351. And like actually, 1 comma 1 is an exception, like it is an edge case because um, 1 comma 1 is itself a minimal coprime because GCD of 1 comma 1 is 1, but it won't happen in any other case, right? So except for 1 comma 1, all of the other are just R minus L. The answer for them is just R minus L, right? So yeah, that was the solution. Like, and as you can see here that in case of 1, if L equal to 1, then the pair changes. Like it is not 1 comma 2, but it is 1 comma 1. But still, there are R minus L pairs, right? In this case also there are 10 pairs. I mean, wait, 9 pairs. 10 minus 1, 9 pairs, because 1, 2, 3 up to 9, right? So you can just take the input of L and R and print R minus L. Other unless R and L are 1. If they are 1, then just print 1. Okay. So I'll just show you the code. Uh, it is not okay. Yeah. So I just took the input of L and R. If L and R are both 1, then just print 1. Otherwise, print R minus L. Okay. So this is the code. So does anyone have a doubt in this problem? No. Okay. So I don't see any doubts in the chat. So I will move ahead to the problem number B. Okay. Okay. So this is called subsequence update. You are given an integer sequence a1 to an and a segment l comma r. You must perform the following operation on the sequence exactly once. Choose any subsequence of the sequence A and reverse it. Note that the subsequence does not have to be contiguous. Okay. Formally choose. Okay, this is formal definition of subsequences and how to reverse subsequence. But we all know what is a subsequence, right? A subsequence is just not like it doesn't need to be contiguous, but it has to be in same order, right? For someone who doesn't know, like I'll explain. For example, if the array is 2, 4, 3, 5, 1, then a subsequence of this would be 4 comma 5, like these and this, the subsequence. Or maybe it can be 1, like just 1, or it can be 2, 3, 1, etc. Okay. So yeah, so basically what we can do is we can choose any subsequence of a and reverse it, right? So basically we and the objective is find the minimum value of al to ar ka sum after performing the operation, right? So the problem, I'll just repeat, I'll frame it in my own words. So we are given an array a1 a2 up to al, up to an, and also we have been given an l to r range. Okay. So we want to minimize the sum from al to ar, al plus 1 up to ar, we want to minimize. And for that we can use one operation. Operation is choose one subsequence and reverse it. And subsequence is that, um, like it doesn't need to be contiguous, right? So anyways, I'll actually tell you what I thought, okay, and then I'll tell you how to solve it, right? So when I was solving the problem in the contest, I actually noticed one thing, that okay, so what is the length of this segment? Length of this is al plus 1 up to ar, right? I mean, this is the segment, so length would be r minus l plus 1, and we can only rearrange the elements in this array, right? So actually what we can observe is that if we can just take the minimum these many elements, if we take the minimum r minus l plus 1 elements and try to arrange them in this subsegment, then that is optimal, right? We cannot make the sum less than that. Like if we try to do that, then we cannot make the sum less than that. So I just check the samples, that is it possible for all the samples at least. So I found out that yes, it is actually, like in all the samples they have given such that the answer is correct. Like basically this 1 1 ln r is 1, so the length is 1, so the minimum element like 1. Okay, and that is the answer. Like basically I was trying that, suppose this is the array and this is the segment that we have been given, right? So this has 3 elements, so my answer would be sum of minimum 3 elements. Like I was trying to do this, right? So like I thought that maybe this is correct, but actually it is not correct. Like I thought of a counter test case, all right? So maybe, like I'll just show you what I thought, like what is a test case. So actually, okay, so suppose there is a 1 here, is it 1 2 1 2 2 1, and the l comma r is given in this range, right? So in this case you cannot put those two ones here. Like it is not possible to use that operation and put these two ones here. Like you cannot reverse any subsequence, right? So this is why that logic fails here. So in case you submitted it and got wrong answer on pretest 2, this is why you failed, right? So now you know. And okay, so Now what we do, like now what I thought was, let's think about the problem, like let's think about the operation. Okay, so let's say this is the given array. Okay, I tried to make a diagram and visualize the problem, right? So this is the array, this is L to R. Let's say this is L to R. Okay, and let's say I make an operation, like in an operation I can choose a subsequence, right? So let's say I choose this, I choose one from here, two from here, and two from here. Okay, then if I reverse it, so whatever I haven't chose, like I haven't chosen, they won't change, right? These two values will remain the same, but this subsequence will get reversed. So like let's say initially it was something like a b, uh, just a second. Yeah, so let's say initially they were like a b c d e. The numbers are a b c d e. So after reversing, what would they become? It would become like a b c d and e, right? So as you can see that this c actually did not change, but instead of b, d came here, right? So like that is the observation, like basically, as actually you have to minimize the sum of this segment, right? So that's why I am looking at just this segment, that how did it change. So initially it was b here, but now d came, right? So actually whatever numbers are here, their complement in the array will come there, right? Basically the complement of c is just c, complement of b was d, and complement of a was e, right? So whatever the numbers were there, their complement will come, right? So actually the thing is that we cannot take numbers from both the sides of the array. That's the thing. Like basically, I'll just show you why. Let's say I want to take one number from here. This is a, and this is b. Let's say that I want both of these here in my array. So actually it is not possible. Okay, why? Let's say I want to remove these. Let's say this is e, or let's say this is z, and this is y. So they are very big numbers, so I want to remove them, like I want to replace them with a and b. Okay, but I can't do that, because let's say I replace y with b, that means the complement of y is b, right? So the center of the subsequence would be somewhere around here, right? Like between y and b. So definitely the complement of z would be even further, right? In my subsequence, the complement of z would be even further. And let's say I try to replace z with b, like if these two are complements, then the complement of y will be like inside here. It cannot be a. That's my point. Do you get it, guys? That z and b, if they are complements, then y and a cannot be complements, and if y and b are complements, then z and a cannot be complements. So my point is that you can never swap, like you can never bring in two numbers from two different sides. Okay, I'll explain with example. Someone wants example, so I'll explain with example. Okay, so let's take an example. Let's say we have 100, we have 1, then we have 100, 1, 100, 100, and 1. Sorry, wait. We have 100, 1 and 100. Okay. So this is the array. Now, and L comma R is given to be like this. Okay. So L is 3 and R is 5. This is L, this is R. Okay. So ideally, what I would want is that I have these three ones, this one, and this one. This one is already in here. So I want these two ones to come in my L to R segment, right? But how can I do that? Actually, I cannot do that. Why? Because see, here I told you that whatever subsequence you take, let's say you take this subsequence, or I'll just explain it one more time using some neat drawing. Okay. So just forget about the subarray for now, like L to R, forget about them. Let's say I am just taking the subsequence, and let's say here the numbers are written 1, 2, 3, and 4. So when I reverse this, what would 1 get replaced with? It would get replaced with 4. So the complement of 1 is 4, and the complement of 2 is 3. So when I would reverse this subsequence, it would become like 4, 3, 2, and 1, right? So as you can see that this drawing is kind of like this. The complements are like this. Basically, they are like this and this, and maybe the someone is a complement of their own. But it cannot be, the complements cannot be like this, right? That's what my point is. It cannot be like this, and it cannot be like this also. Okay. So if I give an example, so basically I want these ones to be here, right? But I cannot have them because, for example, if I try to make the complement of this and complement of 1 to be 100, then I cannot keep the complement of 100 and 1, because in that case, like, this is not possible in a subsequence. They have to always look like this. They have to always look like this. Okay. And so I cannot swap them, but I can always swap any number from one side. Like, for example, my point is that I can swap any number from a single side. Let's say this is L to R, okay, and let's say I want these two numbers to be here, right? Then I can just pair them like this. Okay, so when I reverse this reverse subsequence, they would reach here. And let's say I don't want these two, I want this and this. Then I'll just pair it like this. And let's say I don't want two, I just want this one from the outside, and I want this one from the inside. Then I can just pair it like this. So these two will get swapped. So my point is that either from the left side you can take the elements into the subarray, or from the right side you can take the elements into this subarray L comma R. So is this part clear? Like, how, what is a complement? How how I am defining it, and why it cannot be like this? Why it has to be like this? So any doubt in that part? Okay, so the thing is that basically we have been given this range L to R, and we can either um, like take elements from the left side or the right side. So actually, to solve this, basically we can, what we can do is we can just separately take a look at this subarray. Okay, and then we can take a look at this subarray, and just take, like, just look at the minimum three elements. So for example, if I take, um, let's give a good example. So let's say we have 5, 10, and 1. Then here we have 2 and 3, and here we have like, let's say 2 and 1. Okay. So basically you want these three, you want three elements, right? Sum of three elements. This r minus l plus 1 here is equal to 3. So in this red subarray, you can look at the minimum three elements. So what are they? They are this, and this. So what I can do is I can just pair this 3 with 5 and pair this 2 with 10. And I can reverse the subsequence so that 1, 2, and 3 become in my subarray. So basically, the minimum three elements from this subarray I can take. So that will give me an answer of 6. But if I take the minimum three elements of the blue subarray, let's say I take the minimum of this blue subarray, then what are the three minimum? This 1, 2, and 1 are the minimum, which will give me an answer of 4. So I can actually pair this with this and this with this. So the answer is 4. Like basically, I just look at the red one and the blue one, look at the minimum three elements of them, and print whichever the sum is minimum. Okay. So that is the implement, like that is the solution here, and I'll just show you the code. So if you guys have any doubt in the logic or the code, just let me know in the chat. Right. So I took the input of L and R. Then like I made it zero indexed because it was initially one indexed. Then this is IA. IA stands for input array. Like this is my macro. Now I made two arrays, like this red one and blue one, vector L, B, and C. So I actually, this B is the blue one, B is the right one, and C is the red one. Okay. So from L to N and from 0 to R. And then I sorted both the arrays, and this accumulate function is for calculating the sum. So I calculated sum of the first R minus L plus 1 elements, and I just printed the minimum of sum 1 and sum 2. Abdul, you might have taken sum as int, not LL maybe. Like okay, so if what about non-contiguous? Like this actually covers all of all of these subsequences. So like my point is that whichever the minimum elements are there in one side, they may be non-contiguous, right? That's why you would have to use non-contiguous operation in that. Like if the minimum were somewhere around, let's say this is L and R, and the minimum are here and here, then you would have to use non-contiguous operation. All right. Okay, so let's move on to the problem C. If someone has a doubt, then you can just ask me in the comments. I'll reply there. Okay. Uh, yeah. So the problem C today was, okay. So you are given a tree of n vertices. You must perform the following operation exactly twice. Select a vertex V and remove all the edges incident to V, and also the vertex V. Okay. So in one operation, you can just select a node, right? You can just select a node of a tree and delete that node and its incident edges. So after deleting this node, this tree will look like uh, just these three disconnected nodes, right? And you have to do it like twice, two times. Okay. Please find the maximum number of finite components after performing the operation exactly twice. So we have to find the maximum number of finite components. Okay. So so basically the problem says that there's a tree, right? I'll just draw a tree. All right. And in one operation you can delete a node. Suppose you delete this node, then all the edges inserted into it will also delete, right? So it will become like this. And let's say you delete one more node, let's say you delete this node, so the tree will look like this. So this tree has three components, right? So that is like, and we have to maximize the number of components. Yeah, basically we have to choose two nodes such that the number of components is maximized. Okay. So like, so okay, we have to maximize the number of components, right? So actually the first thing to observe here is, suppose you have a node, right? Now there is this component, like I am drawing a tree, okay? So I'm just focusing on one node. uh, so I mean, this big node is a whole subtree, right? Basically there are some more nodes inside it, but I'm not drawing them, abstracting them kind I'm just abstracting them, kind of, okay? So like these big nodes have a subtree in them, or all right. So if you delete this node, let's say you delete this node, right? Then what would happen, that these four subtrees would become independent, right? So it will kind of become like this: 1, 2, 3, and 4, right? You just deleted this node and its edges. So now there are four components. Initially there was only one component because they were all joined, but now this tree has four components. Okay, so it is not a tree anymore, it is a forest. So as you can see now that when you cut from a vertex, like when you cut a vertex, its degree, so this vertex degree is 4, right? So when you cut it, the number of components would be equal to its degree. Like since it had 4 degree is the number of edges that is adjacent to it. So the number of edges in it is 4. So if you delete this vertex, then the number of components would become 4, right? That is one observation here. So some of you might have done like, okay, so some of you might have thought that probably we need to remove the maximum degree first, right? You want to remove the maximum degree. That's what some of you might have done. Like you are given that tree and you find the node with maximum degree, right? So in this case, it is this node right here, the central node. It has a degree of 6. So first you must have taken this node and deleted it. So now actually we have 6 independent components after deletion. Okay, 1, 2, 3, 4, 5, 6, right? And then you might have deleted the in the new tree the vertex having the second most highest degree. So like all of the remaining ones have 0 degree, but these two nodes have 1 degree. So you delete one of these nodes, right? So you delete this node and this edge. So that's what you might have done, right? And then you might have gotten wrong answer. So how many of you did this? That you first took the maximum degree of the tree, and then out of, like in the remaining tree, you found the second highest degree. Yeah, so you might have gotten wrong answer, and so the reason that you got wrong answer is because this logic is wrong, obviously. So actually, why it is wrong, I'll just show you a test case in which it is wrong. Okay. um okay, let's say this is 1 2 3. This node is numbered 1, this node is numbered 2, this node is numbered 3, and all three of these nodes have a degree of 4, right? This is 4 degree, this is 4 degree, and this is 4 degree, and all the other nodes have a degree of 1. So maximum degree here is 4, right? Right. So basically, so which 4 to delete? This 4, this 4, or this 4? So if your code actually deleted this 4 first, this 4 first, then it is wrong, because let's see what is the answer if you delete this 4. Okay. So I'll just delete this 4. uh, there's one node here, so I deleted this 4. Okay. So now there are 4 components, as we expected, and now its degree is 3. These nodes degree have degree 3, and these have degree 0, right? All right. So now what you do, you just take a degree of a node of degree 3 and delete it, right? So you delete this node. Okay. So now you count how many nodes are there, or how many components are there. One component is this, one is this. Okay, I'll use a new color, right? So one component is this, one is this, one is this. I'll just erase the degrees. One, one, and one. So in this case, there are 1 2 3 4 5 6 components, right? But actually, this is not optimal. Why? I'll just show what is the correct answer here. Okay, I'll show you. So this is our tree. Now, if I delete this node first, okay, so these edges would delete, and this edge would delete. And now, what I do is I delete this node. So in that case, these edges would get deleted, right? So this has how many? Um, 1 2. Okay, I'll make a line here. 1 2 3 4 5 6 and 7. 7 nodes, 7 components, right? So that's why this answer is wrong. Your solution is wrong. So actually, the greedy doesn't work here. Like, actually, when I gave the contest, I did not think of this approach. So I did not have to think that why it is wrong, because actually what I did, it is very like rigorous. Okay, I have a proof for it as well. So I'll just show you what I did. All right. So okay, let's assume that you have a tree. Now we know the formula for one node, right? Like if I delete one node, then how many components would the tree break into? Like if I delete this node, let's say this node is V, then the number of components after I break this node, that is the degree of V. Like that is equal to the degree of V, right? So we know the formula for one node. We know the formula that how many components there will be for one node, right? So I tried to actually derive it for two nodes. All right. So yeah, let's see how we do that. Okay. So let's say we have these two nodes. Like there is a big subtree here. There's a big subtree here. A big subtree here. Wait. And a big big subtree here. Okay. So let's say I delete this node u and this node v. Okay. So what would happen? Now if I delete this node, let's say I delete u and v. Let's say first I delete u. Okay. So first what happens is these components get disconnected, right? So now this graph has three components, right? And then I delete this v. So now, actually, say these two components are independent. Like these two will be there. But now, what if I delete v? So this one component will convert into three components, right? So what will happen? It will look like this. If we delete this, so we will have total five components. So my point actually is that the formula is like I will try to derive it in a more intuitive fashion. Okay, this is u, this is v. Now, actually, let's say the degree of this node is u. Like this is the degree of this node is degree of u, and this is degree of v, right? So when I break this node, when I delete this node, the graph will convert into degree of u number of components, right? And one of those components has the vertex v, right? So when I delete this, this breaks into three components because in this graph degree of u was 3. Now I delete this v. Okay, so in that case the component which had v, it got broken into even more. So the component which had v, initially it was just one whole component, and now it got broken into degree of v components, right? So actually the number of components increased by degree of v minus 1. Okay, so initially it was degree of u, and then it increased by degree of v minus 1. So total finally it is degree of u plus degree of v minus 1. But actually this is only when u and v are not adjacent. Like initially I drew the graph like this, right? This is u and this is v. So in between there is one node or maybe one component, entire component. So actually I drew this by for purpose. Like I did not draw u and v in adjacent by like deliberately, because if they are adjacent then the story kind of changes. Okay, because see here if I delete this u, then this component and this component remain, and then when I delete this v, these two components remain. So actually the answer is degree of u plus degree of v minus 1. But let's say u and v are adjacent, there like this component was not there. Okay, so I'll just show you how that works. If u and v are adjacent like this, let's say this is u, this is v. So if I delete this node u, then what will happen? This will happen, right? And then I delete this node v, so this will happen. Now as you can see there is no middle node here. When u and v were not adjacent, there was another middle node here also, but now it is not there. So actually in this case there is one less component as compared to the previous case. So in the previous case the answer was degree u plus degree v minus 1. But if they are adjacent, so this is for non-adjacent. Okay, non-adjacent. But for adjacent it will be even less than, like it will be even less. Degree of u plus degree of v minus 2 for adjacent. Okay. So this is what the formula becomes. Like in case of just one node, it is just degree of v, right? If I just delete this node v from a tree, then the components would be degree of v. But for two nodes, I derived this formula, that is degree of u plus degree of v minus 1 if they are non-adjacent, and if they are adjacent, then the formula is degree u plus degree v minus 2. So did everyone get the intuition for this formula, or do they want me to explain once again? Okay, so if you got it, then now the problem just becomes trivial. Like basically, you want to maximize the value of just one second. It got zoomed out for some reason. Yeah, so you want to maximize the value of degree v plus degree u minus 1 if u is not like u and v are not adjacent. So u and v are not adjacent to e, or degree v plus degree u minus 2 if u and v are adjacent. So actually this I'll first tell you how to check for the second case. Okay, like basically there are two cases, right? So how to check for the second case? Degree of v plus degree of u minus 2 if u and v are an edge. So for this actually we can just iterate over all the edges, right? There are n minus 1 edges. So there are n minus 1 pairs which are connected, right? There are n minus 1 u comma v which are connected. So we can actually iterate over all of them and check that what is the maximum value for this expression for them. Okay. So in the adjacent case, it is fine, right? Now, if I think about what if they are not adjacent, like I want to maximize this value if they are not adjacent. Okay. So technically, it's like there's an array. Like you can think about this problem, right? There's an array. Let's say this is the array of degrees 2, 5, 3, 4, uh, 6, 10. Like I'm not sure whether this degree is possible or not. Like if a tree like this even is possible. But okay, let's just assume that this is the degrees of the nodes. Like this is node 1 degree, node 2 ka degree, node 3 ka degree, and so on. And so now you basically have to maximize degree of v plus degree of u minus 1. So ideally, what you would do? Ideally, you would just sort this array, or like basically you would just find the two maximum elements, right? You want to maximize degree of u plus degree of v. So you would just take the maximum two elements, right? So you would just take this 10 and this 6. But here the constraint is that what if they have a common edge? What if this 5 and 6 are connected? Like you can't do that. Basically, here there's an additional constraint on u and v, that u and v should not be connected. U comma v should not belong to edges, right? So actually, there are many ways to do it. What I did was, I think the most simple. I just sorted the array. Okay, so I just sorted the array. So it looked like this: 10, 6, 5, 4, 3, and 2. And I also kept the indices with them, like I made a vector of pair. Okay, so this 10 was belonging to 6, 5, 2, this 4 was of 4, 3 was of 3, and 2 was of 1. Okay, now what I did was I just iterated through the array. Like for this 10, I am checking, like for this 10, I am checking the first node, which is not a neighbor. Like, see, I took this highest element as 10. Now I check that which is the highest element, which is not a neighbor of 10. I mean, a neighbor of 6, right? This 6 has the highest degree. So I check the first element, which is not the neighbor. So let's say 6 comma 5 are neighbors. Then let's say 6 comma 4 are 6 comma 2 are neighbors, and 6 comma 4 are neighbors, right? So I check that 6 comma 5, okay, I can't take that. 6 comma 2, I can't take that. 6 comma 4, I can take, right? 6 comma 4, I can take. So I just check that, okay, 14 can be my answer. Like this 10 plus 4 minus 1, sorry. Degree of u plus degree of v minus 1. 14 minus 1 is 13. 13 can be my answer, right? So one of the possible answer is this. Now when I find this 4, which is not adjacent to 6, I don't move on. Like I won't go on to 3 and 2 also, because I found this 4, which is higher than 3 and 2. So that's why I sorted the array in the first place, right? So my point is that this for this 10, I will iterate through the array, and I'll check that what is the first element which is not adjacent. Then I'll do the same thing for this 6. Like I'll, let's say 6 and 5 and 2 are also adjacent, let's say. And so I'll go to this 4, and I'll see that, okay, 5 and 4 are not adjacent. So I'll see that 6 plus 4, 10. 10 minus 1, which is 9. That is also a possible answer. Like I'll keep a variable ans, and I'll keep taking max with it. Like I'll keep doing ans is equal to max of ans comma whatever degree of u plus degree of v minus 1, right? So I'll do this. So I'll just run a for loop. I'll run a nested for loop, and but I'll break as soon as I find an index which is not adjacent. So some of you might think that why isn't this code O of n square? Like I am having a nested for loop, right? For this 10 also I am going till the whole array. Then for this 6 I am going till the whole array. So isn't the time complexity O of n square? Isn't it O of n square? So can anyone tell me why it is not O of n square? It is O of n into degree. I mean, yeah, I get your point. Like it is, like for each element, like for this 10, at max I will skip like degree times. The degree of 10 is, I mean, so degree of 6 is 3, right? The degree of 6 is 3. These 3 are edges of 6. So I'll at max skip 3 vertices, right? Now for this 6, its degree is, I mean, for this 5 vertex, its degree is 1. So I'll at max skip one element. So actually, in total, I am just skipping sum of degrees. Sum of degrees elements. Like that's basically, if I see that there's an edge between these two vertices, then I'll skip that vertex, right? So this skip operation, I actually do it only degrees at maximum degrees times. So definitely the sum of degrees times it will be less than that. Like my complexity is O of sum of degrees, and sum of degrees will be like 2n minus 2, right? So that's why it is O of n. Okay, so that is the logic here, that first we check the adjacent cases. That for that we'll just iterate over the edges, and for the other case where they are not adjacent, we will try to just iterate over all the possible, like we'll just sort the array, we'll sort the degree array, and for each element I'll find the first next that is not adjacent to it, and I'll break there when I find it, right? So actually you can just um, use a set of edges, like you can just use a set of pair, like you can store the edges in set of pair of int, and you can just check in login time that whether an edge is there or not. Ujjwal didn't get. So which part didn't you understand? So I'll try to elaborate that part. Okay, Ujjwal doesn't seem to be responding. So I can we take max node limit 300? Sorry, like I don't get your question actually. I think this is a very particular doubt. So let's just move on. You can ask me in the comments and I'll reply. Okay, we'll talk in the comments. Don't worry. So I'll just show you the code for this problem C that I implemented. Okay. Yeah. Okay. So I just input the edges, like I just store them in a set of pair, so that I can easily check whether an edge exists or not. Okay. And I've also made a vector of degree, like I'll just count the degree of each node. So I took the edge a and b, I inserted, and I increased the degree of a and b by one. Okay. Now I have answer, that is like the answer, which is maximum possible number of components, right? Now I just made this vector of pair, which is like this vector, like which I want to sort. So I will, this is the sorted thing. So I am making this vector of pair, right? So b dot pushback degree I minus one, sorry, degree I plus one comma I plus one. Like from one to n, I am pushing, I am inserting the degree and the index, right? And then I'll just sort this b vector, reverse sort, like reverse sort the b vector. Okay. And then um yeah, for int I equal to 0, I less than an I plus plus. So this is the macro for that. For int I is equal to 0, I less than an I plus plus. So I iterate over all the nodes, right? 10, 6, 5, 4, 3, 2. And then I iterate from I plus 1 to n. Like in this vector I'm iterating. Like, so initially I am at here. The I is here, and then j will start from here. It will starting from here. This, if this is in this set, then it will go to this, then it will go to this, and so on, right? So um, I just did j is equal to I plus one, j less than n, j plus plus. If edges dot find bi dot second, bj dot second, like b dot second stores the index, right? So if there's an edge, I mean, if there's not an edge, like if edges dot find is equal to edges dot end, that means that this edge is not in the set MP is make pair. Okay, make pair. So if edges dot find make pair edges dot end, then that means this particular edge is not there in the graph. So actually we can just set the answer to max ans comma the degree of j plus degree of I minus 1, right? Degree of u plus degree of v minus 1, because they are not adjacent. And then we just break. We break out of this for loop so that we don't have O of n square complexity. We have only O of n, right? I mean O of n log n if you count this find thing, like it takes log n time, right? And yeah, this is for the second case where they are not adjacent. And for their adjacent, if they're adjacent, then I just iterate over the edges. For that case, I'll just iterate over the edges, and I'll just do degree of x dot first plus x dot second minus 2, and I just print the answer. Okay, so is this clear? For adjacent, this is the code. Like I just iterate over the edges, right? I'm iterating over the edges, and I'm taking the maximum with answer, and like the answer for that would be degree of u plus degree of v minus 2. So Akshat, I hope your doubt was this only and I cleared it. Yeah, okay. Cool. All right. So in if you don't have any other doubt, then we can move on to the problem D. Just disclaimer that I currently don't have the code for D. It is giving some minor, like it is getting wrong answer on test 7. So I'll debug it soon, and I'll post the link on the description of this video. Okay, but I have the logic and it is correct. Okay, so I'll explain the logic right now. All right. So yeah, the problem says that there are m plus n distinct points a1 0 a2 0 an 0 and b1 comma 2 b2 comma 2 and bm comma 2 on the plane. Initially your score is 0. To increase your score, you can perform the following operation. Choose three distinct points which are not collinear. Okay. Increase your score by the area of the triangle formed by these 3 points. Then erase these 3 points from the plane. Right. So basically, we have some points. Like a nice visual is given here. We have some points on one line and some points on the other line. And we can choose 2 points from one line and 1 point from the other line. We can make that triangle, and our score increases by the area of that triangle. And then we just delete those points. Okay, let kmax be the maximum number of operations that can be performed. For example, if it is impossible to perform any operation, kmax is 0. Additionally, define fk as the maximum possible score achievable by performing the operation exactly k times. Like if we perform this operation k times, then what is the maximum possible score? Here fk is defined for all integers such that 0 less than kmax. Find the value of kmax and find the value of fx for all integers from 1 to kmax. So basically the problem says that we can just choose 3 points, two from one line and one from a different line. Then we can make that triangle, and we can add the area of triangle to the score, right? And we need to maximize the score using k operations. So we want to tell the maximum score using k operations. Okay, so I'll just try to give an intuition about this thing. Right. Okay. So first of all, what is the area? let's figure that out. So this height is equal to 2, right? Now, um, let's say we have these 4 points. This is called A. Like this is A0, or let's say A1, A1, A2, A3, and A4. This is B1, B2, B3, and B4. Okay. So let's say I take this B1. Let's say I take 1 point from this upper line. I take B1, and I take A1 and A4. So guys, what is the area of this triangle? What is the area? Uh, Half base into height. Yeah, that's correct. So in this case, the height is 2, right? The height of this triangle is just 2 because these lines are parallel, and the base is A1 to A4, right? So the area is just A4 minus A1. No, you don't need to use Heron's formula. Just half base into height. That will work because the height is always 2. So the triangle's area is A4 minus A1. Okay. Is this greedy? Actually, like, a greedy thing is there in my solution, but it is not completely greedy. We have to do some computations. Actually, there exists a greedy as well, but I don't exactly know what how that works. So I'll tell you my solution um, that I have the proof of also. Like, why it is correct, I have the proof also. So I'll tell you that solution. And I don't know the greedy one exactly, so I can't tell that. All right. So anyways, this is not completely greedy. What I am telling you, it is not completely greedy, but okay. So yeah, the area of this triangle is A4 minus A1. All right. Now, actually, what we have to do is we have to maximize our score, right? We have to maximize our score by performing k operations. So what is score? Score is just A4 minus A1, the summation of this, right? Basically, um, like, if we take this triangle, then the score would be this, and then after that we have to delete these points, right? So let's say we delete this A1, A1, A4, and this B1. Okay. Then let's say I choose these two, A2 and A3, and I choose, let's say, suppose B3, right? So in that case, the answer may, like, in the answer, A3 minus A2 would get added. So so initially it was A4 minus A1, then A3 minus A2. Okay. And after doing this, suppose we delete these 2 points as well, A2 and A3, and this I delete this B3. So actually now we have no points on the A, like we don't have any points on this axis, right? So we cannot do any more operations. So our answer for this operation, like if we do it this way, it is equal to this thing right here. Okay. So actually, as you can see, when I'm doing an operation, technically just feed it like this way. Okay. That I have to, let's say I choose, this is A, this is B, this is line A, this is line B. Let's say I want to choose 2 points from line A. Okay. And 1 point from line B. So whatever point I choose from the line B, let's say I choose this B3. Okay. So that B3 was this. I chose this B3, right? So whatever I choose on the B axis, that point just gets wasted, right? Because there is no contribution of B3 to this A3, like area, right? The area doesn't depend on B3. So whatever I take, whatever point I take, let's I take B2, or I take B4, or I take B1, whatever point I take, uh, it won't affect the area, right? So basically we can just take anything, we can take any point from the b axis. So technically what we would want is just to take the useless point. Like we will just try to take the useless point, that which doesn't have any benefits. Okay, so kind of just think that, right? Now let's say I tell you that I want to do just one operation. Okay, so I have these 4 points on both axes: a1, a2, a3, and a4, and we have this b1, b2, b3, b4. So let's say I tell you that what if I want to find the answer for k equals 1? Like I just want to do one operation. Then which point would you choose? Like which points would you choose to maximize your answer? How will you maximize the answer? I think it is pretty easy. I don't need to ask you guys. So either you take this, like a4 minus a1, or you take this length b4 minus b1, because you cannot get any higher length than that, right? You cannot get more length than that. Max and min points, exactly. So whichever is higher, you will just take them, right? Now let's say I want to check for k equal to 2. Okay, so actually that case is somewhat a bit complicated. So actually I'll simplify it by saying that I want to do two operations on a. Like I want to do both, like I want to do two operations, and I want to do both of them on a. What I mean by that is I want to choose, like, see, in each operation I choose 1 point from one line and 2 points from the other line. So I want to choose 2 points from a and 1 point from b for both of these operations in, right? Okay, so how would you choose these points? Tell me. So what I can do is, so actually what I can do is I can take maybe a3 and a1 first, or let's say I can take a1 and a2 first, and then maybe I can take a3 and a4. Okay, so in that case my score would be a4 minus a3 plus a2 minus a1. So actually instead of writing like this, I will make you visualize it. Okay, so this is a number line, right? This is a1, this is a2, a3, and this is a4. So if you take like this, then the score would be whatever I am drawing in blue. It would be this length and this length, right? The sum of these two lengths. So is this optimal? Like, can you do any better? And if yes, then how would you do it? A4 minus A1 and A3 minus A2. Yes, correct. So if you take A1 and A4 together, then you will get this length as an answer, as your area, and then you will get this length as your answer as well, right? So actually, it is much better than previous case. In the previous case, we were just getting these two. So yes, take the farthest points, exactly. So you can just take the farthest points, and now let's extend this to like 6 points, let's say. So if you had 6 points, 1, 2, 3, 4, 5, 6, and you had to choose, and you had to do three operations on this, then, or let's say we have 7 points. Okay, so if you have 7 points, then the most optimal way is to do this: 1, 2, and 3. And this is a waste point, we don't have any use for it. Okay, so basically if you want to do three operations on a, then you would do it like this. That's my point. right? If you want to do three operations on A, then you would do it like this. But how will you know that how many operations you want to do on A, right? Like basically, I want the answer for K operations, right? I want the answer for K operations total, right? So that means total on A and B. On total A and B, I want to perform K operations. So, um, how would I know that? Like, how would I know that how many to apply on A and how many to apply on B? Like, which one will give me an optimal answer? Like, suppose I want to apply X on A and K minus X operations on B. So we don't know, right? We can't know that how many operations we have to apply on each. But let's say if we knew that we have to apply, let's say, two operations on A and five on B, like if this is the optimal for K is equal to 7, like we want to find the answer for, let's say, K equal to 7, and we knew somehow that this is optimal, then easily we can find out that what is the answer, right? Because from A we will just choose the two farthest points, 1 2 3 4 5 6. So we'll choose the two farthest, and let's say from B we want to choose five pairs, then from B also we'll choose the five farthest points. So we will, like, so that's how we can actually find out that given that how many operations you want to perform, how what is the answer, right? So I'll just I'll try to formulate it. I'll make a formal thing, right? So basically, let's say you have this a1, a2, a3 up to an. Okay, a1, a2, a3 up to an, right? So you have n points, so you can actually only take up to n by 2 pairs from it, right? You cannot take more than n by 2 pairs, because in each pair there are 2 points. So gif of n by 2 you can take. So for the first operation you will take an minus a1. Okay, so the answer for the first one, what is it? The answer for the first one, like if you want to find that in one operation what this is the maximum answer we can get. So in one operation actually we can just get an minus a1. Then what about in two operations? In two operations we can get even this pair also. So we can get like an minus a1 plus a n minus 1 minus a2, right? This is 3. This whole was 2. This is 3. And like as you can see that, okay, so this is 1. For 1 it is an minus a1. Then for 2 it is equal to 1 plus something, right? The value of 1 plus this extra thing, an minus 1 minus a2. Then for what would it be for 3? For 3 it would be the answer for 2 plus the third highest gap, an minus 2 minus a3, right? So actually you can see that this is a prefix sum kind of, right? Like you can easily compute this array, right? You can easily compute this array. And for now I'll call it what I have called it in the code. So I'll just check the code what I have called it. Okay, I have called it SA. Okay, so basically SA of I tells you that what is the highest score if you make I operations on A. All right, so this array you can easily make. You can just use the last element, right? Like this is basically a prefix sum kind of thing. You can do a prefix sum approach, so you can easily make this array. And also you can make this array for b. You can make sb of I, like for the same b array, right? So now if I ask you that if I want to make x operations on a and k minus x operations on b, then what is the answer? So the answer would be sa of x plus sb of k minus x, right? So we want to find an x. We want to find an x such that this whole expression is maximized, right? So to do that, actually we need to first find out the range of x, right? Like from where to where can x be, right? Because we have limited number of options, right? We have limited number of points, so we cannot just take, like for example, if I have um let's say I have 4 points on a and 2 points on b. So actually I cannot take x equals to, suppose I want to find the answer for k equal to 3 or k equal to 2, then actually I cannot take x equals 0. I cannot take x equal to 0, because what would that mean? That means that I am choosing 0 pairs from a and k minus x, which is 2 pairs from b. But actually there is only one pair in b. This is b, this is a. So there is only one pair in b. So how would we actually choose two pairs, right? So basically there is some range for x. There is some range for x for which it is possible to choose, right? Like for which these values make sense. So I'll try to find that range. All right. Now how to find that range? You can actually do something like, okay, so a has n points, right? B has m points, a has n points. Okay. Now let's say you want to do an operation on n p times. Like on a I'm doing p times, and on b I'm doing q times. Okay. Or let's just say x times and k minus x times. On a I am doing x times, and on b I am doing k minus x times for some k. Like if I want to find the answer for some k, then I am doing it k minus x times. So so guys, tell me that what are the constraints? So of course x has to be greater than or equal to 0. X cannot be negative, obviously. And since we are saying that we are doing k minus x on b, that means k minus x also has to be greater than or equal to 0. Like if you think about it, if you are total, you have to do k operations, and out of those k you are doing x on a, right? So x has to be less than or equal to k, right? So that's why this k minus x greater than or equal to 0 comes, right? So first of these two conditions are there, right? But actually there are more conditions, right? Because these points are limited. There are n points on a and m points on b. So since these points are limited, actually we have to look at them also, that we have to set an x such that these points are not all utilized. All right. So actually if we are doing x times on a, okay, so from a, wait, so when I'm doing on a I'm doing x times, right? So from a, 2x points will be gone. 2x points from a will be chosen, right? Because I am doing this operation on a, so I am choosing 2 points from a and 1 from b. So if I do it x times, 2x points from a would be gone, and x points from b right? This is due to the operations that I did on A, right? Now, when I do on B, so I do k minus x on B, k minus x operations on B, right? So 2 into k minus x points from B and k minus x points from A will be gone, right? These many points will be gone in these. So in total, how much are gone? In total from A, due to the operations on A, 2x plus like 2x due to the operations on A, and due to B, k minus x. So this is equal to like k plus x, right? And from B, how many are gone? From B, like it is x plus 2k minus 2x, right? So for B, it is x plus 2 into k minus x. So this is equal to 2k minus x, right, guys? So actually, we want that both of these values should be less than or equal to the points that they have. Like we have only n points for A, right? So we cannot remove more than n points. So both of these values should be less than or equal to n and m. This should be less than or equal to n. This is less than or equal to m. So from here, actually, we get that. From here, we get that. Okay, x is less than or equal to n minus k, and from here, we get that x is greater than or equal to 2k minus m. Right, guys? So these are the third and fourth conditions. And first two we had x greater than or equal to 0 and k minus x greater than or equal to 0. So if I just combine all of these four, what can I write? See, I'll just write them again here. One was x greater than or equal to 0, and second one was x less than or equal to k. So if I combine these four inequalities, then what will I get, guys? So first of all, I'll take these two, like x has to be greater than or equal to 0 and x has to be greater than or equal to 2k minus m. So basically it has to be greater than the max of these two, right? Whatever is bigger, it has to be greater than that also, right? So max of 2k minus m and 0. X has to be greater than this. And less than or equal to k, less than or equal to min of k, comma n minus k. Right, guys? So actually this is the range of x that we need to check, right? So basically what I can do is I can run a for loop from k, like okay, actually what will happen when k is too large? When k becomes too large, actually this term will dominate, right? 2k minus m will be larger, so the lower limit will be 2k minus m. And what about the upper limit? Min of k comma n minus k. So n minus k will be the upper limit. But when k is too large, then basically this lower limit will actually be greater than the upper limit. So basically, if suppose you take a k which you cannot do, then it will happen something like the condition will become 4 less than or equal to x less than or equal to 3. So basically this lower limit will be greater than the upper limit. So at that point you will know that you have to stop, and that this is the maximum k that you can take, right? So actually I'll just iterate from k is equal to 1 to what to whatever, like till whenever this condition is applied, till whenever this condition breaks, right? So I'll just iterate from k equal to 1 till whenever this condition is not breaking, right? No, we don't need to do BS on k because we need to print all the values on k, right? We want to print the answer for all k. So we have to iterate on all k, right? We have to iterate on all k. But now the real question here is, how do we find the answer? We found the range for x. Like for some k, we found the range for x, where x is the number of operation on a, right? So we found the range for x. But how do we know that in this range, which x should we take for the optimal answer, right? So which x should we take for the optimal answer? Now that is the question that we want to answer. If we just iterate, if we just nightly iterate over these two, like if we iterate in this range, then it will be like too much of too much of a computation, right? It will result in O of m into n, which is sorry, O of m into n, which will give TLE, right? But this is there's an observation here. So what is the observation here? It is actually how these functions work. Like okay, the answer. What is the answer? Like for x, some x, the answer is just what did I call the arrays? Like these arrays, I call them SA and SB, right? So if we do x times on A, then the answer is just SA of x and plus SB of k minus x, where x is in this range, right? In this range, x should be. So we have to find the maximum value for every k of this thing, right? So these arrays are actually kind of like functions, right? So actually, you need to um, observe one property, like how are they constructed. Let's think about that. How are they constructed, right? So actually, I'll just look at this SA, okay, and similarly, I'll just say for SB. So SA, how is it constructed? SA is constructed like okay. So we had some numbers on this array: A1, A2, A3, A4, A5, and so on. A4, A5, A6, and A7. Right now, actually, to calculate SA1, what we did, we just did A7 minus A1. Then to calculate SA2, we added to SA1, we added this A6 minus A2. Now, obviously, this A7 minus A1 is greater than A6 minus A2, right? So, actually, if you think about it very closely, you can actually think about it that how will this function look like? Okay, so initially, if we do zero operations, it is zero. For zero, it is zero, right? Then for what is it for one? For one, it is this thing, right? For one, it is a7 minus a1, right? So basically it increased by a7 minus a1. Then for 2, what will it be? Like this is 2, right? So for 2, what will that be? It will like the increase. What will be the increase in the function? The increase would be a6 minus a2, right? So from when we went from 0 to 1, the increase was a7 minus a1. Then for 2, the answer is a7 minus a1 plus a6 minus a2, right? So the answer increased by a6 minus a2 when we went from 1 to 2. Now, when we are going from 2 to 3, then what will the increase be? The increase would be like a 5 minus a3, right? So actually, as you can see that the first increase was a7 minus a1, which is this length right here. See here. Then 6 a6 minus a2, which is a shorter length. right here. Then the increase is a3 minus, sorry, a5 minus a3, which is the shorter length, even shorter length, right? So as you can see that this function is increasing, but the rate of increase is decreasing. See, the function initially it is at 0, then it increased, then again it increased, but not that much. The change has decreased, you know. Then again it increased, right? But not that much. So basically it is convex down. You can actually see that it is kind of like this. It is convex down. Its concavity is downwards, right? So do you guys understand like this, that this function are actually concave down? Like it increases, then it increases a little, like but less, then it increases even less. So it looks kind of like this, right? So this is what um this essay looks like. Okay, so this is what SB also looks like. SB also looks like this, because SA and SB are just similar. So SB also looks like this, right? How will that help? That is a good question. Like it will help. I will tell you how will that help. Okay, so we can see that they are convex down, right? SA and SB are both convex down. So okay, now what was our answer? Our answer was SA of x plus SB of k minus x. So this is the graph for SA of x, right? But let's say I want the graph of SB k minus x. So if I want to draw the graph of this, then it will just be like shifted and flipped, right? It will something look like this. This is x equal to k. Like you understand, right? Because whatever value at x equal to k, like 0 was occurring in SB of x, if I put x equal to 0, then it is same as putting x equal to k in k minus x, right? So if I draw the graph of SB of k minus x, then it will look like this, right? So now actually this is also convex down. SA of x is convex down, and SB of k minus x, that is also convex down. So actually if I add both of these functions, if I add SA of x plus SB of k minus x, then this is also convex down. This function in x is actually convex down. So basically if I want to plot this function with respect to x, so with respect to x it actually looks like this. It is convex down, right? And at 0 also, no, okay, 0 at 0, so there is some value, so it is something like this. It is convex down. That's my point. So basically there is one edge case here. And actually the range of x is not 0 to k, right? The range of x is actually smaller than that. The range of x is this, to max of 2k minus m comma 0 to min of k comma n minus k. So actually there is some range of x which is valid. So suppose this range of x is valid, right? So I'll erase the other part. So this is actually the range of x which is valid. So in this range, our graph looks like this. So there is some maximum value, there is some value of x. There is some optimal value of x for which this graph attains its peak. Like it is the maximum value. it is not a parabola, but it is like similar to a parabola. It is not quadratic functions graph, but yeah, it is convex. That's my point. It is convex down. So basically, you have this range. You have this L to R range, which we just computed, and we want to figure out that what is the maximum value in this range. Okay. So okay, how do we do that? That is the main question here. How do we figure out the maximum value? So actually, um, there is something known as ternary search. Like guys, have you heard of binary search? Of course you have heard of binary search. So that is applied on monotonic functions, right? If a function is monotonic, if a function is monotonic, like this. Okay, so let's say you want to find the first point at which it is greater than k, the first point x at which it is greater than k. Then you can apply binary search, right? You can just apply binary search. Like let's say you have this active range. Let's say you have this range L and this as R. So you will check the middle. So mid is this, right? So you will check this point. This is greater than K. So you will move R to here, right? And then again you will check mid. And in this case this is less than K. So you will move the L here. Like this is the binary search that you can do, right? But in case of monotonic graph. But in case of a convex graph, you can actually do ternary search. Like this is actually a very nice method to find the extremas of a convex function. Like basically the task here is that we have a convex function, right? From some L to R, we have a convex function, and we want to find out that okay, what is the maxima point? What is the point of this maximum? We want to find out this x. So how does this ternary search work? Actually, it works like, let's say in binary search you take a middle, right? You take a midpoint. But in ternary search you take two mids. Like this range is from L to R. So you will take one point at one thirds and the other point at two thirds. Okay, so actually the exact coordinate would be just like 2L plus R by 3. 2L plus R upon 3. And this coordinate will be L plus 2R upon 3. Okay, so you take these two mids, mid 1 and mid 2. All right, I call them mid 1 and mid 2, right? Although they are not mid, but okay, anyways. So you will take these two mids, okay, and then you will um check their value, right? So you check their value. So value at mid 1 is this and value at mid 2 is this, okay? So basically we can see that f of mid 1, the function of mid 1, is greater than the function at mid 2 in this example, right? Is greater than function at mid 2, right? So actually if this is the case, then you can say that actually you can say that you can change r equals to mid 2. uh, Wait, let me think. If function of mid 1 is greater than function of mid 2, then it might happen that this is the case, or it might happen like this is the case, that this is mid 1 and mid 2. So yeah, you can change r equal to mid 2. Like you can move r to mid 2, because if f of mid 1 is greater than f of mid 2, like this is the case, right? So x can never be greater than r. Like I'll give you a feeling of this, okay? How should I give a feel? Let me think. So this is a convex graph, right? Now if f of mid 1, f of, let's say this is L, and okay, not L, um let's say f of a and b. I'll just take a and b. This is a and this is b. So if f of a is greater than f of b, that means that either this is the case that a is here, b is here. So x is somewhere around in middle. Like, so basically x is not beyond b, right? Or it can be like both a and b are on the same side. Like, it can be like this. This is the maximum. Sorry, this is the maximum, and a is here and b is here. So this can be also the case. But in this case also, this x is not greater than b. So we can actually reduce our search space to just r equals to b. Like, we can put r equal to b if fa greater than fb. Right? Similarly, if fa is less than fb, if fa is less than fb, then what can happen? Let's say um, let's say this graph is skewed, right? The graph is something like this. So um, a is here and b is here. So fa is less than fb. So in that case, we can say that L equal to A. Like, X is definitely greater than A. So we can update our search space to A. Like, L equals to A, right? So if FA is less than FB, then we can update L equals to A. If FA is greater than FB, then we can update R equals to B. And if FA equal to FB, then we can update both. We can update L equals to A and R equals to B. Like, if I show you why, if this point is unique, like this top point is unique, right? So if fa is equal to fb, then that means that one of them is here, other one is here. This is a, this is b. So you can actually update that L and R. L is equal to A and R equal to B, because our x will be between those two things. Okay. So this is how you can actually do ternary search, and this will also give you the answer in logarithmic time. Why? Because after each step, we are actually decreasing our search space by 2/3. Like, see, initially the search space was this, right? Let's say the initially search space was this whole L to R. Then we find A and B, right? Then either we do L equals to A, that means either our search space gets turned down to, sorry, gets decreased to this. Wait. So either our search space changes to this, or it changes to um, this thing, red thing, or it changes to, like, in the best case scenario, it changes to like this yellow thing. So actually, in each case, initially, if the length was, let's say, len, then it will become at most like 2 by 3 of n. In the best case, it can also become length upon 3. So as you can see that in each step, it is getting down by a ratio. So you will, so the time complexity that it would take would be just log of initial range, initial range to the base 3 by 2. Like, binary search is also log range, initial range to the base 2, because in each step in binary search, the space is halved, right? But in this case, the space is becoming 2/3, not halved. So it will take some more time. The base is 3 by 2 here. So actually, moving on to the question, you can actually do ternary search on X. And okay, one thing to keep in mind is that when these L and R become very close, like, see, let's say L is equal to 4 and R equal to 6, then probably when you apply the formula, you will apply the formula that A is equal to 2L plus R upon 3, right? So that will give you like, it will give you 4 only. And when you apply B is equal to L plus 2R upon 3, So it will give you 4 plus 12, 16 upon 3, which is 5, right? So A is equal to 4 and B is equal to 5. Then let's say you get that FA is less than FB. So you will just update L is equal to A. But the thing is that L is already equal to A. Like, since L and R will too close, and we are working with integers, right? So that's why, is if FA is equal to FB, FA is less than FB, sorry, then L is equal to A again will happen. So nothing will happen actually. So you are stuck in an infinite loop. So actually, to handle this, you can just ensure that this gap doesn't go less than 2. Like, whenever it is less than 2, you can just break out of the loop and check all the values. See, basically, when L and R are far enough, let's say L and R are like 4 and 7, so they are 3 away, so they are far enough. In this case, we will get A is equal to 5 and B is equal to 6, so no problem. But as soon as they come, like R minus L less than or equal to 2 हो जाए, so at that point you should break out of the loop and just check all of the remaining values for the maximum value. Like, you have only three values remaining, right? Like, if we have 4 to 6, then just 4, 5 and 6 you have to check. So just do that through a for loop. Otherwise you will get stuck in a infinite loop. Okay. So yes, in the question we actually had a range for x, right? We had this range for x, 2k minus m comma 0, that is the lower limit, and upper limit is k comma n minus k. So we can actually do ternary search in this range to get the maximum value of sa of x plus sb of k minus x, right? So this concludes the solution, and I would show you the code, but it is like it is giving wrong answer on test 7 for some reason. So actually, I'll just show you the idea. Like, I'll show you the code, but something is wrong in it. So if you can spot it right now, then just tell me. And otherwise, I'll go through it. I'll check the code and I'll update the link in the description, and I'll make a comment that what was wrong actually in the code. Okay. So um, for now, I'll show you the code, the current code, which is almost correct, right? So otherwise you might have some difficulty if I don't tell you the code and I just send the solution. So I'll explain the code also. Okay. So first I take the input. This is just the input taking. Then I sort the arrays. This is important because in the problem these arrays not sorted. I don't know why, but it is not sorted. Then this vector of sa and sb. Sa and sb are like these vectors, SA and SB. The maximum score for A and maximum score for B. If you do I operations, SA of I is that, okay. And to like compute them, I just make the array and take the prefix sum. Like, what I do is, let's say I have the array. Um, I have A1, A2, A3, A4, and A5. So I actually just pushed, like, initially in the array there was 0. Then I pushed A5 minus A1. Then I pushed A4 minus A3. So currently this is the array. A4 minus A2, sorry. A4 minus A2. So currently this is the array. And then I just take the prefix sum of the array. So when I take the prefix sum, it will become like 0, A5 minus A1, A5 minus A1 plus A4 minus A2. Right? So that's what I did. That's what I did. Okay. So I just did it using 2 pointers. I put 1 pointer on A1 and 1 pointer on A5. Okay, so I just computed this SA and SB. Like, right here, I'm pushing this into the vector, and in this for loops, I am just taking the prefix sum. All right. Uh, yeah. So now I make a vector for the answer, like what I have to print. Okay. Now I make a for loop for k equal to 1, k plus plus. Like I don't put a condition here. I just check that if low is greater than high, then I'll just break. Like this low is uh, this range for x, right? We computed this range for x. Where is the range? Yeah, so this range for x we actually computed. So I did max 0 comma 2k minus n and min k comma n minus k. So this is the lower and upper limit. And if low is greater than high, that means that that k is not possible. So I just break. So whatever is in the ans vector, I'll just print that. And let's say if it is possible, then I just do ternary search on it. So while high minus low greater than equal to 3, I just found out the mid one, which is 2 into low plus high by 3, and mid 2 is low plus 2 into high by 3. Then I found out the answer for mid 1 and mid 2. Like the mid one was, the answer for mid 1 is SA of x plus SB of k minus x, right? So answer for mid 1 is this, answer for mid 2 is this. If they are equal, then again, that is the case when FA equal to FB. So when FA equal to FB, then you can just do um, this, like low equal to mid 1, high equal to mid 2. And if FA is less than FB, then high is equal to mid 2. And if FA is greater than FB, then low is equal to mid 1. All right. Is this the mistake? Wait. If FA is less than FB, then um, the peak is at here, right? So the low is equal to A. So for some reason I have done the opposite. So maybe that is the mistake here. I'll just check. Okay. Okay. So for some reason it is going into an infinite loop. Let me think why that is the case. If FA is less than FB, the function is like this, right? The function is like this. So if FA is less than FB, that means that my x cannot be before A, right? So L is equal to A. In this submission, V1 and V2. Okay, I have to check what. Oh wait, I saw the mistake. This should be SA, right? My bad. Mid V2 should be SA of mid 2 plus this. So now let's try to run it. Okay, wait. V1 is less than V2. It does not appear to be running. Okay, let's just leave it for now. I will correct the code in just like 5 to 10 minutes and I'll make a comment on the YouTube video. Okay. So yeah, this is the ternary search part, and this is a typo. I'll change that. All right. And yeah, so basically this high minus low is now less than 3, right? After the ternary search we did, this high minus low is less than 3. So now I just make an answer variable to, and I just take the max. Like I'll iterate from low to high. I is equal to low, I less than equal to high, I plus plus. So basically I'll just check all the values in the remaining range, and I just say ans equal to max of ans comma sai plus sb k minus I, right? So in this range, whatever is the maximum answer, I just push that into the ans variable, and then I just print the ans. Okay, thanks Harshit for the compliment, I guess. Diwakar has a doubt in problem number B. Um, so does anyone have a doubt in D actually? Before that, before I tell you, before I tell the doubt for B, does anyone have a doubt in D? They can ask right now if they have a doubt. Meanwhile, I'll try to run this. The max number of operations will be min of n plus m by 3 comma n comma m. Yeah, that makes sense. I mean, that is not necessary. Like, I did not use that fact in my proof, but it makes sense. Like, basically, you want the k max, right? Like, in from this code, it automatically just computes k max without us having to think about it. But if you want to compute k max, then we can compute k max. Like, you have to see. So this is B. This has m points. Okay, 1, 2, 3, 4, 5, 6, 7. Let's say, and this is A. Let's say this is only 1 point. So in this case, this A is the bottleneck right here. This A is the bottleneck. So we can only do one operation because we can just take two from B and one from A. So in this case, A is the bottleneck. Then let's say in other case, B has one operation. B has one vertex. Okay, and A has 7 vertices. Then in this case, B is the bottleneck, right? B is the bottleneck. But what if both are enough? Like, let's say that both have 4 4, or let's say both have 6 6, 4 5 6, right? So then if we apply x operation here and k minus x operation here, then in total we we apply k, right? We apply k operations, and in each operation we we take out 3 points, right? So in total we take out 3k points. So that has to be less than or equal to m plus n, the total number of points that these two lines have. So the k should be less than or equal to m plus n upon 3. So actually we have these three bounds. One bound is this, and the other bound comes when one of the lines has way less points than the other one. Like, if this has only 1 point, then this is the bottleneck. So that's why we just take m plus n by 3, comma m, comma n. You just take the min of these three. Yeah, okay. So if anyone doesn't have any other doubt, do you have any other doubt? Okay, if you don't have any other doubt, then I'll just end this stream. And after, like, I think 10 15 minutes, I'll. Okay, also, like, ternary search sometimes gets stuck in local minimum maxima. Reason for that is wrong answer on test 7. Um, but there is. Okay, I see what you are saying, but that shouldn't be a problem, I think. Like, if I think what you are saying is one of the things, like, if the function is like this, that our range is already on the maximum. Like, if this is our range L comma R, and this is already the maxima, but in this case also I think it should be working. Like, This is A, this is B. So FA is greater than FB, right? So in that case, we would just do R equals to B. So basically, this R actually comes closer to L. So in each iteration, it is coming closer to L, and it will converge to this point only. So I don't think this should be a problem. Yeah, it is like a step function only. Like it is discontinuous. Like it is not, of course, it is not continuous. It is only defined on integer values, but still, it is convex. Like the consecutive difference decreases. I mean, it is not continuous, but it is convex, and we can always apply ternary search on convex functions. But yeah, keep in mind that you cannot apply ternary search on functions like this, like which have equal value on multiple points. Basically, let's say you have kind of like this. We have this. The function looks like this, and like these 3 points are on the same line. I mean, these have the same value. Then in this case, you cannot apply ternary search because it will get messed up. Like basically, you can only apply ternary search when the function is strictly convex. Like at every point, the change is not non-zero. It is either positive or negative. But actually, in this problem, the functions SA and SB, the functions SA and SB are actually not like this. Like they are definitely decreasing or increasing. So I don't think that is a problem here. I'll figure it out and I'll let you guys know in the comments. All right, and I'll update the link in the description. All the four links I'll send in the description of this YouTube video after like some time. All right. Okay, then if okay, yeah, Diwakar had a doubt in problem number B, right? So Diwakar, you are saying that sort the array and take the first r minus l plus 1 nums. So I already told that it is not right, because Diwakar, if you are there, then just tell me. Then that how will you do in this case? The array is 2 1 1 2 and l is equal to 2, r is equal to 3. So basically this is the l and r. Sorry, my bad. I am My brain is somewhat tired right now. This is the array, and um, this l is equal to 2, r is equal to 3. So how do you plan to get both of these ones here? What operation will you do so that they come here? How will you ensure that? Okay, I think Divakar has got his answer. Someone wants me to explain Kevin and puzzle problem. I Okay, like if you have some doubt, then you can DM me on Codeforces. We can discuss there. I can't discuss it right now in this live stream. Sorry about that. All right. Anyways, so if no one has any more queries or doubts, then I will take your leave. And thanks, guys, for watching. Thank you, guys, for listening and staying till the end, whoever stayed till the end. I hope I was clear in my explanations. And yeah, see you next time. Bye, everyone.